Section 4.6 covers another way of solving the same kind of equations that show up in section 4.4. So second order, constant coefficients, and non-homogeneous. There are situations where you could go either way, where given one of those types of equations, it might be one where either variation of parameters or undetermined coefficients are going to be about the same in terms of length and difficulty and all that. But there were some that we couldn't do in section 4.4. Like with the trig functions, you could only use sine and cosine. Here you can do things like tangent. And so then if it was one that had tangent on the right side of the equation, then this is the route that you'd have to take. There are also ones that sometimes are shorter this way. They tend to be the ones that are sort of long and drawn out, maybe a product of two different forms on the right side. And that's actually what example 3 is like in this section. So we're going to see that too. But if you look here, it's the same basic setup. The second order, constant coefficients, non-homogeneous. And the first part, when you get the complementary solution, that's exactly the same. The only thing that's going to be different here is the method that you would use to get the particular solution. So here's that. To find y sub p, if I scroll down a little bit here, if you look at this, where there's this assumption that y sub p is u1, y1 plus u2, y2, if you look at that and think, that kind of looks like the first step when we did reduction of order, yeah, it does. And that's sort of the point. It is pretty similar to that, except that now we already know what two of the solutions are, and we're trying to get a third one, essentially. So the y1 and y2 come straight out of the complementary solution. So you'd have to get that first in order to form the general form of what the particular solution is supposed to look like. Then in order to figure out what u1 and u2 are supposed to be, you could get it by solving this system of equations here, which our book brings that up and talks about that. If you want to see it, it's there. I figured that wasn't worth replicating in a video because most people just kind of jump to, okay, how do you actually get u1 and u2? Which is also the way that I look at it. So down here, this is how you get them. So u1, it's the integral of the negation of g of x, so the g of x being the thing that's on the right side of the equation instead of a 0, times y2 over a, where a is just the coefficient of y double prime, times the Wronskian of y1, y2. And then u2 looks kind of similar, except that there's no negation in the numerator, and there's a y1 instead of a y2. Those have the potential to get ugly, and I guess if it was a situation where it was an either or, where you could either use this or use undetermined coefficients, then maybe you go the other way. But the ones that we're going to have here aren't too bad, and I think the ones that are in the book for this section that I put on the problems list aren't too bad either. And then lastly, this thing in part 4, those are indefinite integrals, so there's that natural reflex to put in the plus c at the end. But you don't have to. If you don't put in the plus c at the end, then you'll just get the particular solution. If you do put in the plus c at the end, then you'll get the whole thing. So you would get the entire solution, so complementary plus particular. And in the first example, I kind of went through it both ways. So then that way I can kind of point at it and go, look, this is what happens when you do this. All right, so this first example, if we want to find the general solution of y double prime plus 2y prime minus 3y equals 2e to the 3t, hopefully it looks kind of familiar. It's also in section 4.4. And I wanted to have the first example be one that was one that we already had, so I could point at it and go, look, it actually works. So that's kind of what this example is. And this would be one where you could go either way. And I think with one like this, because what's over here on the right side is not super complicated, I think you'd actually be better off doing this with undetermined coefficients, to be perfectly honest. But just to run through it once with one that we already kind of know how it works, or where we know what we're supposed to get at the end, I figured that was worth it. So just like with undetermined coefficients, first thing you're going to start off with is you get the complementary solution. So there's my homogeneous analog with the 0 on the right, auxiliary equation, And you go, okay, yeah, that's factorable. You could either lambda is equal to -3 or lambda equals 1. And then there's our complementary solution, c1 e to the -3t plus c2 e to the t. Okay, nothing new yet. And ignore this cloud over here for now. We'll get to that at the very end. So for now, I'm just going to pretend it's not there. All right, so then the next thing to do is to get the particular solution. And so we're going to need a y1 and a y2, and they come straight out of the complementary solution. So I just said, okay, there's y1, the e to the -3t, and then there's y2, e to the 3t. You don't have to do it where you just basically chop off the arbitrary constants, but that would be the simplest thing to do. But if you really felt like it, you could say that you wanted y1 to be 4e to the -3t instead of just e to the -3t, and this would still work. You'd be making things harder on yourself, but you could do it. Let's see. So then what we're going to end up doing, we've got our particular solution. It's going to be in this form of u1y1 plus u2y2. So I just have this double underline here, meaning like this is some mystery right now. The thing would be multiplied by e to the -3t. And this is also some mystery over here. The thing would be multiplied by e to the t. We're going to need the Wronskian because it shows up in both of the things that we have to integrate to get u1 and u2. So I figured, okay, might as well go ahead and get that early because we're going to need it twice. All right, so there's y1, there's y2, and then there are their derivatives underneath. And then the Wronskian, so using the diagonals, that diagonal, upper left to lower right, is going to be e to the -2t. And then this one would be -3e to the -2t, so we're going to subtract that. So minus a minus is a plus, right? So plus 3e to the -2t, we get 4e to the -2t. There's our Wronskian, so then we should be able to get u1 and u2. Might as well just put the whole thing up here now. All right, so u1 and u2, they're pretty similar looking, right? You're subbing in g of t in both, and then for u1, you're going to put y2 there, so that's why I've got the e to the t right here. A is the coefficient of y double prime, which here that's just 1, and then the Wronskian that we just got, the 4e to the -2t, right? There's that. And with this one, you can say, well, if we simplified this, -2/4 is -1/2, so I pulled that out front. And then you end up with e to the 4t divided by e to the -2t. And if you subtract exponents since you're dividing, you'd have 4 minus -2, which is 6. So that's where I'm getting that e to the 6t. And then if you integrate that, you're going to end up with 1/6 e to the 6t. So multiplying 1/6 by -1/2 will give you that -1/12. And then I have the plus C1 circled in a different color, even though the scan doesn't really make it look like that different of a color. The main writing's supposed to be in blue, and then those circles are in black. I mean, I guess at least the circles look like they're black, but that blue looks really dark. But anyway, I circled these because you don't really need them. And if you don't put them there, that's where you just get the particular solution. And then that's how I kind of handled it when we get down here. But if you do include them, that's what that cloud up toward the top of the page is about, which we'll get to at the very end. But U2, similar idea, right? You're going to sub everything in, right? I guess you're subbing in a y1 this time, so there's the e to the -3t. And then simplifying this one, we can pull 1/2 out instead of a -1/2 this time. And then you end up with basically just an e to the 0, so just a 1 on top. And then, so the e to the -2t, just bring it up. So you got a positive exponent. And then integrating that, it's going to be 1/2 e to the 2t. 1/2 times 1/2 will give you that 1/4. So 1/4 e to the 2t, and then if you want to add on the plus c2, you can. But then these two pieces right here would be enough to give you the particular solution. So if we go down here, right, there's the general format of it. So then I just sub in, there's my u1, the -1/2 e to the 6t. There's y1. Then u2 is 1/4 e to the 2t, and then there's y2. And then if you simplify this thing, -1/12 e to the 3t plus 1/4 e to the 3t. And so that's -1/12 plus 3/12, which would be 2/12 or 1/6 e to the 3t. And so then the general solution would still just be y sub c plus y sub p. So complementary solution plus particular. And so then there's y sub c, those first two terms, and then y sub p on the end. All right. Then going up to that cloud, what's in the cloud is what happens if you include C1 and C2. Then with the general solution, I'm still just subbing in what I had for U1 and U2. I just have the C1 and the C2 in there as well. And so then I guess I have to distribute, right? And you end up here, we have the negative 1/12 e to the 3t plus C1 e to the negative 3t plus 1/4 e to the 3t plus C2 e to the t. And then combining like terms, so the 2 e to the 3t terms, there's that 1/6 e to the 3t. And then there's y sub c, those last two terms here. So you do get the same thing, ultimately, right? It's just that if you include those arbitrary constants, then essentially you'll get the full solution rather than just the particular solution. And that's just a matter of preference. Neither way is right, neither way is wrong. They both go to the same place, so I guess really they're both right. Maybe that's a better way to put it. Number 2 is one that you could not do using undetermined coefficients because of this, because it has tangent. And with undetermined coefficients, we could only have sine and cosine as the trig functions. So here, this is the way you'd have to do it. All right, well, I guess let's start going. So first, y complement, pretty easy with this one. So y double prime plus y equals 0. Right, there's our homogeneous analog, and we say, all right, well then our auxiliary equation would be lambda squared plus 1 equals 0. So lambda is plus or minus I. So y complement c1 sine x plus c2 cosine x, or I guess the other way around. If you wanted to have c1 cosine x plus c2 sine x, that would be fine. And then we just say, all right, well then if y1 is sine x and y2 is cosine x, then we can get the Wronskian, right? Derivative of sine is cosine, derivative of cosine is negative sine. So then we get negative sine squared x minus cosine squared x. So that ends up being negative 1, right? Just using the trig identity, we can get that down to something nice and simple. All right, then getting the particular solution. All right, well, we'll have to get U1 and we'll have to get U2 just like we did before. We're going to do that integration. I'm hiding it right now, I guess in the sense that you can't see it on the screen, but U2 is a little bit long. U1 is nice though. So for U1, sub in tan x, right? That's our g of x. That's what's on the right side of the equation. Y2 is cosine. And then a, the coefficient of y double prime is 1. The Wronskian is negative 1. You can say, okay, well, we have a negative over a negative, so those are going to cancel out. And tangent times cosine is just sine, so we're really just integrating sine. We go, well, that's negative cosine. And then plus c1 if you want it. Here I tried doing it in a different color. That plus c1 is supposed to be purple. I don't know how well that's actually coming out though. Y2, the integration happens to be a little bit longer. There it is. Okay, so with y2, we're going to sub in tan x for g of x, and now we need y1, which is sine x. And I brought that negative out front, and then I rewrote tan as sine over cosine, which is how I'm getting the sine squared over cosine. And then this is the part that you kind of just have to remember, I guess, when these sorts of things come up. Even if you just remember, like if you were doing homework, if you just thought, I know that there's a trig function in the front or back cover of the book that should work, right? As long as you see that sine squared x and that function's like a trigger, like, okay, that's a thing. There's something that I can do with that. Maybe that's enough. But really, this is just using that sine squared plus cosine squared equals 1. And then I just kind of wrote it so it only had cosine. Like that's what I was shooting for. I wanted an expression that was just in terms of one trig function. So there is an identity where you can jump from there to there, but that's not really the way that I think about it, I guess. But then from this step to this step, basically I just factored out a negative 1 out of the numerator. And so then that way out front would be negative 1 times negative 1. So it's just a 1 because I thought this would be easier to handle. But then if we break that up into two pieces, cosine squared over cosine is just cosine. And then 1 over cosine is secant. And then we can break that into two integrals. So integral of cosine minus integral of secant. Integral of cosine, that one's easy. It's just sine, right? The integral of secant, that's one where if you multiply the top and bottom by secant x plus tan x, you get something where you can use the natural log as the integration because the derivative of tan is secant squared and the derivative of secant is secant times tan. So that's what I used there. And that's how I've got this natural log right here. It would be the natural log of the absolute value of secant x plus tan x. So there, I guess that one is actually the one that's more of a trig maneuver. But that's one of those ones where if you don't remember that that's what the integral of secant is, you can manufacture it if you just kind of think like, okay, well, what are the trig functions that have secant in their derivatives? And then from there, you end up thinking about secant and tan. You can kind of piece it together. That's really the way that I do it still. I still kind of derive it every single time. And then there's that plus C2 if you want to include it, but you don't have to. Then the particular solution, so negative cosine x times sine x, then plus cosine x times this thing right here, so sine x minus that natural log. And then we do get some things to add out because we're going to have minus cosine x sine x plus cosine x sine x, so those are gone. And all we're going to be left with is the negation of cosine x times the natural log of the absolute value of secant x plus tan x. Therefore, the final overall solution where we add the complementary and particular solutions together, there's our particular solution. And then there, or I'm saying this backwards, there's the complementary solution, the c1 sine x plus c2 cosine x, and then there's the particular there, minus cosine x times that natural log. So that's one where you would have to do it this way. You couldn't possibly do this one using undetermined coefficients. Number 3, this one you could do using undetermined coefficients, but I think it would be longer. Because up here, you've got the product of two of the forms that you could use for undetermined coefficients. But then you think, well, with that x squared, we have to have ax squared plus bx plus c, and then d e to the negative 2x, which you could simplify down to where you only had 3 undetermined coefficients, and you could write it as ax squared e to the negative 2x plus bx e to the negative 2x plus c e to the negative 2x. And then you could do all 3 of those individually and combine it together at the end. So you could do it that way if you wanted to, but I think this is shorter. I didn't actually try it the other way, so I could be wrong, but I have the impression that my intuition is right, considering it would be 3 individual pieces that you'd have to cobble together at the end. That feels like it would not be short. So I think this would be the way to go with this one, where it would be one you could do either way, but I think using variation of parameters here, you'd probably be better off. So first, y complement. This is one where you get a repeated root. So there's our homogeneous analog auxiliary equation, and you go, yep, that's a perfect square on the left side. That's lambda plus 2 quantity squared. So lambda is equal to 2, and that's a repeated root. So our complementary solution will have c1 e to the negative 2x plus c2x e to the negative 2x, right? That's the way that we handle the repeated roots. Then we want to get the particular solution. So we'll just say if that's y1, the e to the negative 2x, and then y2 is x e to the negative 2x. Then the Wronskian, well, the derivative here isn't too bad. You just bring down that negative 2. This one's a product rule, but still not awful. And then if we get the determinant, so that diagonal minus that diagonal, we end up over here with negative 2x e to the negative 4x plus e to the negative 4x plus 2x e to the negative 4x. So look, we get some cancellation. That's nice. We got 2 terms that are going to add out. We just end up with e to the negative 4x. All right, so once we have that, we get u1 and u2, which here they're both nice and short. And the integrals are nice and simple, right? The x cubed, x squared, that's great. So you sub in. Right, so there's g of x, the x squared e to the negative 2x. Here we need y2, so x e to the negative 2x right there. And then a, the coefficient of y double prime, once again, is 1. And then the Wronskian is e to the negative 4x. Here, got an e to the negative 4x on the bottom, got an e to the negative 4x on the top. So that really is just negative x cubed. And I pulled the negative out front. And we say, well, the antiderivative of x cubed is 1/4 x to the 4th, or x to the 4th over 4. And then if you want to add the plus c1 here, you can, but you don't have to. u2, about the same, right? You have y1, so e to the negative 2x. I guess that's different. You don't have the minus here. But you can say, well, we got an e to the negative 4x on the bottom. We got an e to the negative 4x on the top. So those are going to cancel out. So really we just end up integrating x squared, so that's 1/3 x cubed, or x cubed over 3. And from there, not so bad putting together the particular solution. So u1y1 plus u2y2. There's u1, the negative x to the fourth over 4, and then there's y1, the e to the negative 2x. And then u2 and y2, so u2 being the x cubed over 3 and y2 being x e to the negative 2x. And if we simplify that down, we're going to have negative 1/4 x to the fourth e to the negative 2x plus 1/3 x to the fourth e to the negative 2x. Those are like terms. We can combine them together. You get 1/12 x to the fourth e to the negative 2x. So that's y sub p, our particular solution. And so then there's the general solution right there, right? Here's y sub c, the complementary, those first two terms, and there's y sub p at the end. And that's that. So that's one where you could go either way, but I think in this case, variation of parameters would be the shorter way of doing it.